Welcome to Module 5 of Political Statistics. In the last module, we covered distributions, misbehaving variables, logs, centering, and scaling. We spent time discussing the interpretation of transformed variables and worked through an example that helped us understand why these tools and skills are necessary and useful. In this module, we'll use those skills to start understanding the relationships between variables. We'll look at covariance, correlation, how to use the two metrics, and how to interpret them. We'll also spend a little bit of time talking about why covariance and correlation alone shouldn't be interpreted causally unless we have good reason to do so. Let's get started. So far in the class, we've been focused on single variables and have spent a lot of our time dealing with the fact that variables vary, obviously. In our GDP example from the last module, that variance stretched across several orders of magnitude and on a scale that wasn't easy to interpret. So we had to come up with ways of solving those problems and focusing on the relevant range of variation. And if our only interest was to describe and summarize individual variables, those tools would probably be enough. But more often than not, we want to go beyond describing and summarizing single variables. We want to understand what relationship those variables have, or if they have a relationship at all. We're usually not interested in GDP for its own sake, but rather in GDP as it relates to, for example, infant mortality, quality of life, likelihood of protest, or voter turnout. We're not just interested in how these variables vary in isolation, but how they co-vary, how they change with each other. Before we get into measuring that relationship, why don't we take a step back and do what probably comes easier to us right now: visualize. For this module, we'll work with voter turnout data for the 50 United States for the 2020 election. To keep things simple, we'll pick well-behaved variables that are on a nice 0 to 100% scale, measured in our dataset as values between 0 and 1. Our variables are voter turnout as a percentage of the total eligible voters in that state, and the percent of the total state's population that identifies as Hispanic, two continuous variables. First, it might be interesting to see how these variables vary in isolation. So let's make two histograms as we've done in previous modules and see what we get. Okay, so it would seem as if states vary quite a bit in terms of the percentage of their populations that identify as Hispanic, and they vary less in terms of voter turnout, or at least they did in 2020. Another way to frame that is to say that there's a big difference between the states with the smallest Hispanic population, near 0, and the largest Hispanic population, near 50%. But the difference in voter turnout between the largest and smallest turnout states was only between about 55% and 80%. So a 50-point range for the first variable and a 25-point range for the second. And sure enough, if we find the mean and standard deviation for these two variables, we find that the mean voter turnout is relatively high, but standard deviation is low, while the mean for percent identifying as Hispanic is relatively low, but standard deviation is high. Great, we're soaking and poking around in our dataset and have taken some initial steps to describe and summarize it. But now I want to know how these variables relate. How would we go about visualizing the relationship between these two variables? A good place to start would probably be a scatterplot with one variable on the x-axis, in this case percent identifying as Hispanic, and the other on the y-axis, voter turnout. Let's see what we get when we do that. Well, I could draw some lines that would intuitively look like a good match, but that's not really a robust way of analyzing data. And anyway, there are a lot of lines that could look like a good match to these points. What I really want is some way to summarize the relationship between these two variables. That is, as one variable gets bigger, does the other get bigger as well, or does it get smaller? One way to try and answer that question is just to count. Why don't we normalize our variables? That is, subtract the mean from each value and plot this scatter again, but this time with lines indicating where 0x and 0y are. Now we can count how many points are in each quadrant of this scatter plot. We might say that any point in the top left or bottom right quadrant gives us some evidence of a negative relationship. That is, as one variable gets smaller, the other one tends to get bigger, and vice versa. By contrast, any point in the top right or bottom left quadrants gives us evidence that the relationship is a positive one, meaning that as one variable gets bigger, the other one does as well, and as one gets smaller, so does the other one. So we've counted up our points in each quadrant, and now we have a table. Why don't we group those two quadrant groups together, the negative relationship quadrants and the positive relationship quadrants? We find that 46% of our points fall in the positive relationship quadrants, while 54% fall in the negative relationship quadrants. That's not the unambiguous answer we were looking for, but it certainly confirms our suspicion that there's not much relationship between these variables, or that the relationship isn't as simple as one goes up while the other goes down. But in descending the ladder of measurement, we threw out a lot of information. It's not just that we want to know whether a relationship exists, but rather its magnitude and the certainty with which we can talk about a relationship. So how can we use the information we have to construct a more robust measurement of how these variables vary together? We need some way of capturing not only the direction of the relationship, which we did with the above quadrants, but also the size of that relationship. If both variables move together and by a lot, that's different than if variables move together but only by a little bit. Moreover, as with the above example, we want to talk about change relative to the mean value of each variable. Like GDP, some variables are always positive, so if we don't normalize them, we'll never tease out those negative relationships. Let's start simple. For a given observation, we first want to center our variables, so we subtract the mean of that variable from our observation. Now, we have two values that are either negative or positive, one for each of our variables. Next, we want an operation that will preserve the direction and scale. So why don't we multiply these two numbers together? Now that we've done that for one observation, let's go ahead and do it for all of our observations. And since we're interested in the average relationship for our whole dataset, why don't we sum up all of the values that we get and divide them by the total number of observations, just as we would for the mean. The resulting value is called the covariance, and unlike our quadrant example, it gives us information about not only the direction, but the magnitude of our relationship as well. A positive covariance tells us that if we observe one variable with an above average value, we're likely to observe the other with an above average value as well. A negative covariance tells us that if we observe one variable with a below average value, we're likely to observe the other with a below average value too. In fact, you might have noticed that that first step of subtracting the mean from each of our values is very similar to how we calculated the variance in the last module. But this time, since we want to preserve the directionality of the value, meaning is it positive or negative, and we had other mechanisms for penalizing large numbers in multiplication, we didn't square the resulting difference. So the covariance is quite a useful metric, and in this case we end up with a negative covariance, which tells us roughly that if we know that voter turnout in a state is higher than the average, we should also expect that state's percentage of Hispanic identifying people to be lower than average. But the unit is a little difficult to interpret. For what it's worth, The unit in this example is percent turnout times percent Hispanic. I'm not really sure what to do with that. What we need is to put the covariance on a scale that is bound by some interpretable limits. To do that, we can divide the covariance by the product of each variable's standard deviation. This makes it so that the resulting number will only ever fall between -1 and +1, and we'll call that number the correlation coefficient. A correlation of -1 indicates a perfectly negative relationship, while a correlation of 1 indicates a perfectly positive relationship. Note that correlation doesn't have a unit, so we wouldn't interpret it as 0.5 voter turnout, it's just -1 to 1. But the correlation tells us only a part of this story. We might have a large correlation, but that coefficient might be highly uncertain. That is, the coefficient is big, but it's only a rough guide to how any individual observation co-varies. It's useful to know what our certainty is. Though it's an imperfect measurement, we might use confidence intervals to understand our level of certainty. A confidence interval asks, assuming that I'm working with a sample, or some random subset of a larger population of all the units that I'm interested in, and I reran this correlation test many times, each with a different sample, where would most of the correlation values fall? In our case, R chooses those values for us. If we reran this test, where would 95% of our correlation values fall? We can see that they'd fall anywhere between -0.36 and 0.18. That gives us some indication that our correlation coefficient isn't very certain, since it might have been negative under different circumstances, and it might have been positive under different circumstances, or it might have been 0. At this point, if we had spent the first half of the class discussing hypothesis testing instead of getting familiar with more basic and, I think, useful tools, we would talk about p-values and hypothesis testing here. But know that we won't be covering hypothesis testing or p-values in any sort of depth in this course. If you want to understand that topic, you should take a proper statistics course. Because, as I've previously noted, this is a political statistics course. Statistics is a servant of our scientific, theoretical endeavors here, not vice versa. So whatever we do spend our limited time on, it better be useful for furthering our understanding of social phenomena. P-values and hypothesis testing are helpful to know about, no doubt, but they don't make the cut for this class, mostly because their use is diminishing among political scientists. Alright, that's a lot of statistics for today, so let's pivot over to the politics. Consider this week's reading, where the author, Professor Narayani Lasala Blanco, looks at the relationship between a person's house flooding and the probability of them voting. Again, simple statistics tell the story. Tables and basic correlations support the main theoretical idea that the costs associated with voting are easily ignored when political parties spend time and effort mobilizing populations, even when the costs of voting are high and even when the benefits of voting are low. None of the techniques used in this paper are at the bleeding edge of statistics, but they are appropriate for the question being asked, and they illuminate a very counterintuitive result. In fact, you might notice that one of the findings of the paper is that there is no effect of flooding on the probability of voting. Speaking in the language of correlation, we would say that the correlation between inches of floodwater and probability of voting is 0. So while that relationship might not be statistically significant, it is substantively huge. Finding no relationship isn't a non-result if you expected to find a relationship in the first place. Professor Lasala Blanco's paper helps highlight the themes of this course, that the proper use of simple statistics is imperative, and good interpretation relies on our theoretical foundation, not on the statistical techniques that we use. Consider our covariance and correlation coefficients. Nothing about the way that we measured those two things specifically allowed us to interpret the resulting metrics in a directional way. By that, I mean that we can't say voter turnout was lower in this state because the total Hispanic identifying population was larger. This is true in a technical sense, though we may certainly want to interpret the relationship as such. In the technical sense, covariance and correlation only tell us about the relationship between the two variables. If we switched the first and second variables in the covariance formula, we'd get the exact same number. Covariance and correlation aren't causal metrics, and we need to be careful not to make causal claims based on them alone. That's where the political part of this political stats course comes in. If you're a major in political science or sociology, you haven't been reading all of that social theory for no reason. Professor La Sala Blanco's paper makes the causal claim because it's built on a robust social theory that enables a causal interpretation of the statistics used. Social theories are the foundation on which measurement, statistical techniques, and interpretations are built. If we start our analysis with the data, we'll easily be misled. Of course, there are statistical techniques that help us get to causal relationships, and if you're interested in that sort of thing, try taking a class on causal inference. But know that even when using those techniques, it's not enough to just run an experiment. You need to be able to interpret your results in the context of a broader social theory. Let's summarize and conclude for the day. Today, we talked about the relationships between variables. We discussed covariance and correlation, as well as the appropriate use of these metrics and why social theory is important. We briefly talked about making causal claims on the basis of correlation and why you should avoid it. In the next module, we'll go over linear regression. I'm looking forward to seeing you in Module 6.